about multipole radiation, the radiation, electromagnetic radiation that is associated with time-varying multipole moments. Very important topic. And so the context in which we're looking at that is that we have some compact source that's localized, and the sources are time varying. The charge density and the work current density are varying in some way as a function of time. And so the multipole expansion, as you remember from statics, is an approximation. And this characteristic scales that define the approximation here. Well, firstly, we're talking about a source that is localized in some region of space. There's some characteristic size of the source, d. And in addition, things are moving around. There's some characteristic time scales over which things change. So that's time scale is defined as as the time it takes light to traverse that localized source. And the approximation, the multipole radiation approximation, involves two approximations, two small parameters. First one is familiar to us from statics. We're looking at what the fields look like at distances that are far away compared to the size of the source. But moreover, there's a new a new small parameter that comes from this time scale. That is to say that this distance, c times t, is much, much bigger than d. Okay? So let me. This is what I said here was incorrect. Excuse me. What I mean to say here is not c, but v. This is the speed of the charges. Pardon. That is to say, there's some characteristic time scale over which the charges are changing, the charge distribution is changing. And so this is the non-relativistic approximation. That is to say, the speed is small compared to the speed of light. All right? That defines a new length scale in the problem, c times t, which can be thought about for the particular case where we are thinking about oscillating distributions of charges, in which case t might be the period of oscillation of the charge distribution, in which case c over the frequency is like the wavelength of the radiation. So that's an important new time scale that appears in this context. And the multipole expansion then requires that the size of the distribution be small compared to the wavelength of the radiation. Okay? So, because now we have three length scales in the problem, there are different regions in which we have different kinds of solutions. So we have the size of the sample, we have the wavelength associated with the radiation if we're talking about harmonic oscillations, and then we have where we're looking at the field. So the multiple expansion always assumes that we're looking at it far away compared to the size of the distribution, but the solution is equally good depending. There's no requirement that we're looking at the field at a distance that's either big or small compared to lambda. It's just that lambda is big compared to d. All right? So if we're looking in a region that is very close in compared to lambda, but yet big compared to the size of the source, that's called the quasi-static zone. And we saw in that region the fields looked like the same, they had the same form as the static fields, except the strength of, say, the dipole moment might change as a function of time. But the form of the field was the same as the static form. There's this intermediate zone, which is called the induction zone, which things are quite messy, in which we're looking at distances on the order of wavelength. There's nothing particularly interesting to say about that, except it's the induction zone. Most importantly to our context right now is focusing on what's called the radiation zone, which is looking at distances that are large compared to the characteristic wavelength, or if it wasn't harmonic, c times t. Okay? So in that zone, what we showed is that these fields fall off very rapidly, and the remaining dominant contribution is the electromagnetic radiation. That's what dominates at distances far. Everything else falls off at a more rapid rate with r, like 1 over r cubed or 1 over r squared, whereas the radiation fields, if we are talking about a localized source and we're far away compared to that localized distance, will fall off like a spherical wave, 1 over r. And in that context, the intensity falls off like 1 over r squared, which is what we would require to think about this as radiation, in that the flux of the intensity through a sphere is constant. So the radiation just goes on to infinity, no matter how big the radius of that sphere is. And so that is why we associate the fields that fall off for a localized distribution as 1 over r as radiation fields. All right? So these are important. There are these two times, there's time scales and length scales, and where we're looking and getting a feeling for that is important. So we looked at this in the context now of our solutions for the potentials, in this case written in Lorentz gauge, and doing an expansion where these are our small parameters. To lowest order in that small parameter, we found these potentials, and the radiation terms for the electric and magnetic fields. The dominant term in the multipole expansions are these. So the first dominant expansion to lowest order in d over r and d over v times the time scale is this, and that's electric dipole radiation. It's the dominant term. And what we see is that the field here depends on the second time derivative of the electric dipole moment. If I'm looking at it at some observation point x at some time t, then it depends on what the second time derivative was doing at the retarded time from the position of the dipole. This is radiation. It has the properties we expect of it. Firstly, E and B are perpendicular to one another. And moreover, they're perpendicular to the direction of propagation, which is radially out from the source. This is a spherical wave. And the part of the electric field, if the dipole second time derivative, say, is in this direction instantaneously, then there is a part of this vector which is transverse to r hat, and a part that is parallel to r hat, and the radiation part is the transverse part for the electric field. And then the magnetic field is perpendicular, according to E cross B, has got to be in the direction of propagation. And in particular, we looked at the case of harmonic oscillation of the electric dipole moment, say, linear oscillation. In homework, you have the problem of a circular oscillation. So for this case, we say is the real part of some amplitude. It could have some phase associated with it, right? But it's along the line. Then the electric field associated with this kind of electric dipole oscillation, according to the formula that we just had here, is going to be the real part of the second time derivative of this, over c squared r, that's omega squared over c squared e naught perp over r e to the minus I omega t at the retarded time. Okay? So this is equal to the real part of k squared, where k is omega over c, e naught perp over r, e to the I k r, e to the minus I omega t. So what we see, as we discussed, is that the kr is nothing more than the phase shift in the oscillation seen locally due to the time it takes the signal to propagate from the dipole to me. And that accumulates a phase, omega over c times r. That retarded time is nothing more than what we call kr. That's what that means. That's just wave propagation. That's nothing to do with electromagnetism. That's just waves. It's a wave phenomenon. And so this we would call, we meaning the royalty, the complex amplitude of the radiation at the propagation, the part that multiplies e to the minus I omega t. Okay? So again, what we see here is that if we have this harmonically oscillating charge distribution, that the radiation from that is a spherical wave. Remember, that's what we studied in our homework. That's a spherical wave. Falls off like 1 over r. The wave fronts are spherically, are on the surfaces of spheres. But it's a vector wave, which means that it has to be transverse in the case of outside of space charge in free space. And this B naught perp accounts for the fact that only the part that's transverse to r hat is contributes to the strength of the field. Okay? And of course the electromagnetic field in that case would be just equal to k squared e naught cross r hat times e to the I k r over r. That's minus that. Okay, so an important concept here that I want to remind you of is the notion of the differential radiated power per unit solid angle. What do I mean by that? Well, we know, so if I look at S, that's the Poynting vector. The Poynting vector, if I look at, say, well, its time average that tells me about the intensity. Okay? And that's equal to E times 1/2 the real part of E twiddle star cross B twiddle, because that's the right way to do it. So if we plug that in this case, E and B are perpendicular to one another, so this is C over 8 pi, the magnitude of E twiddle times the magnitude of B twiddle in the r hat direction. Okay? And the magnitude of E hat twiddle in this case is the same thing as as it must be for a wave, electromagnetic wave in free space. And that's equal to k squared over times the magnitude of the perpendicular component of this over r. So that means that my wave here is equal to, the intensity is equal to C times k to the 4th power over 8 pi, 1 over r squared, p naught, magnitude of p naught per squared. So as again, to emphasize, if I have a spherical wave, the intensity falls off like 1 over r squared. This let us define, in this particular case, if we have linear oscillation, let me define theta as the, let's say that my, this is the polar angle, the oscillation is along the z-axis, and now I'm looking at the radiation as a function of angle. It doesn't depend on phi. It only depends on theta in this case. So this is equal to, or this is equal to sine squared theta times, what's that? Magnitude of p naught squared. Okay, that's the transverse component. When theta is 0, there is no transverse component. When theta is 90 degrees, it's all transverse. Right? Everyone see that? Okay, so what do I mean by the differential? Well, what I'm saying, we know that if I have a sphere, and I'm here looking at the point of observation some distance away from my oscillating dipole, this is the radius of the sphere, then if I have a little patch of that sphere, which has a dA and an r hat out of the sphere, then the differential power that is radiated through that little patch of the sky dP, not that P is different from that P, is equal to what? Well, it's the flux of the intensity through that area. But dA here, if this is the surface of the sphere, by definition of a solid angle, is the radius squared times the solid angle. That's what we mean by solid angle. Right? That's the definition. Like radians is the circumference divided by the radius. Solid angle is the area of a sphere divided by r squared. So this then, if I multiply that through, since this falls off like 1 over r squared, the differential power here is c k to the 4th over 8 pi sine squared theta times p naught squared d omega. So what we call the differential power per solid angle is dp d omega. And that is equal to c k to the 4th p naught squared over 8 pi sine squared theta. Okay, so it has this sine theta distribution. The way in which the differential power varies as a function of the angles on the sphere is called the radiation pattern. As a function of theta and phi. It varies as a function, generally as a function of theta and phi. Doesn't vary as a function of r because, well, we've already integrated it. We've said the flux doesn't depend on r because it's radiation. So, quite often, this is as we sketched last time, we plot this as a polar plot. And so, for example, this doesn't depend, the radiation is independent of phi, but it depends on theta. And so what you'll see sketched is the strength of this differential power as a function of theta is plotted as a polar plot, which means that as a function of theta, this is the z-axis, we draw a radius or a distance from the origin that is proportional to this. So when theta equals 0, it's 0. When theta equals 90 degrees, it's the maximum value. And in between, it goes like the sine, and it has this kind of pattern. So this is symmetric. Okay, so this is a polar plot. These are not the field lines. Sometimes they get confusing because it kind of looks like the field lines of a dipole. It's nothing to do with that whatsoever. This is just the size of sine theta squared as a function of theta. And this is what's called a dipole radiation pattern. Is everyone clear what this picture is? It's often confusing to people. I'm just plotting the radius from the origin is sine squared theta.
So what are the axes?
It's just looking at this. This is in this case, I'm plotting, as I said, this is x perp. So this is something perpendicular to z, right? And it doesn't matter if it be x or y, because this whole thing is it's like a donut, right? Because it's absolutely symmetric. It doesn't matter where I am. The size of the radiation is independent of phi, but it depends on theta. You've seen plots like this before, right? I'm sure everyone ever knows what the hell they mean, but that's what they mean. All right. Yes?
Is theta taken from the z-axis?
Yes. Yes, I'm sorry, that's correct. Theta taken from the z-axis, pardon me. Yes, thanks. Yes. Okay, so this is the differential power, the power radiated per unit solid angle. We can ask about the total radiated power by integrating over 4 pi steradians. power is the integral over all solid angles of the differential radiated power. So that's the integral C a to the fourth over 8 pi times the amplitude squared, the integral of sine squared theta d omega, which of course is nothing more than d cos theta d phi, which is 2 pi in this case. Okay, so neutral. So we do that integral, and this is equal to 8 pi over 3. And so the total radiated power, time averaged, is equal to C k to the fourth over 3 times the amplitude squared. And this is a form of what's known as the Larmor formula for power radiated. We'll talk about in a moment just about a more general form when we're not just talking about a linearly oscillating dipole, but this is the Larmor form. Notice it's a very strong function of frequency. This is omega to the fourth over 3 c cubed p naught squared. Okay, so if for the same amplitude, the higher frequencies radiate much more power than the lower frequencies. All right. We can write this in a slightly more general form. Let's suppose that I have a charge Q that is moving along some trajectory. Okay? And I want to know, here's the origin. Here is the position of the charge as a function of time. And I want to know what is the electric dipole contribution. So here's a charge moving along some trajectory. And the speed is much less than the speed of light. Okay, never moves, there's never a point in time where the speed is close to the speed of light. And I want to know what is the electric dipole radiation that is radiated by this charge. Well, the dominant term will be electric dipole radiation. And that electric dipole rate we just said was equal to minus the second derivative of the electric dipole moment evaluated at the retarded time from wherever the hell I am, way away from the charge, over C times R, right? That's what we have, and we need the perpendicular component thereof. Perpendicular to me. All right, so here's the origin, here's me, wait, and that's the radiation is going perpendicular to that. Okay, now what is the electric dipole moment associated with this charge distribution?
Just QX.
That's right, q times x relative to this origin. So this is equal to minus q, the position of the charge, second derivative over c r. R meaning the distance from the origin to me. And the second time derivative of the position of charge, of course, is its acceleration. So the amount of electric field that's radiated is proportional to the acceleration that the charge is undergoing. If it's going at a constant velocity, there is no electromagnetic radiation. It's only the change in the velocity, that is to say the acceleration, that gives rise to radiation. So that's minus the q times the acceleration of the charge. Evaluated at the retarded time, the perpendicular component. Okay? So the radiation IC depends upon what the acceleration was at the retarded time. From this, we get the instantaneous Larmor power radiated. So there's no time average in this case. I'm not talking about necessarily an oscillating charge. I'm talking about the instantaneous acceleration, and that is equal then to the factor of 2 then, because we don't take the time average, 2/3 the acceleration squared, no perpendicular component, over c cubed is q squared. And this is often known as the Larmor formula. Probably something you had in your GREs. Lester? Remember the Larmor formula? You've seen it? Maybe forget where the hell it came from, but that's where it came from. Okay. Anybody have any questions so far?
Do you know when did they come up with that?
I don't know the answer to that. There is a simpler derivation. Well, it wasn't until after Maxwell, and this wasn't an empirical formula that was discovered before the connection between electromagnetism and light. So it's a post-Maxwell thing. I first saw this myself as an undergraduate. It's an interesting exercise thinking about the following problem. Suppose I have a charge that's going constant velocity, and then all of a sudden it accelerates, and then it goes constant velocity. So what happens in that case is, well, out here, I think the charge is here. The radiation hasn't reached me, but all of a sudden what happens is, over here is, there's a retarded time kind of thing where all the, of course, you can say right here it accelerated, and all of a sudden the fields have a different nature. They are transverse. this hasn't yet reached me. Eventually, this pulse is going to reach me, and you can estimate how much power is going into this radiation due to this very short time with an impulse of acceleration. That's something that was done by J.J. Thomson, I think in 1911, something like that, 100 years ago. But I think that probably post-dated the solutions to Maxwell's equations. But I don't know. I'll look that up. This is a cute little exercise. I'll send that to you. I'll show you how that's done. All right. So this is electric dipole radiation. And this, as we discussed, is the dominant effect from a multipole expansion. It's the dominant effect when those parameters are small. We want to now look at the higher order corrections. They are either corrections to this in our power series expansion, or perhaps the electric dipole moment vanishes because of the charge symmetry. Perhaps there is no electric dipole moment. And so then we need to think about the next multipole moments as their radiation. For example, magnetic dipole radiation, electric quadrupole radiation, etc. So what we want to talk about now is the general multipole expansion. So this is kind of complicated, and we're going to restrict our attention here to harmonically oscillating distribution. Okay? So we're going to say that the charge distribution of the function of time is oscillating harmonically, which means it itself can always be written this way if it's oscillating at frequency omega with some complex amplitude. And similarly, the current has some complex amplitude. So, in that circumstance, if we go to the Lorentz gauge, and we plug in the solution, and plug in that's equal to the real part of rho tilde x prime e to the minus I omega t minus and A is equal to the current at the retarded time, which in this particular case for harmonic oscillation is e to the minus I omega t minus x prime. Okay? So we just plugged in the ansatz for our oscillating charge, and we see, of course, that what we get is, if we factor out the e to the minus I omega t outside of this, this is equal to the real part of some complex amplitude of the scalar potential oscillating as e to the minus I omega t, and this is equal to some complex amplitude for the vector potential oscillating as e to the minus I omega t. Okay, so my scalar potential in this case is equal to the integral over the source, the amplitude of the source times a spherical wave emanating from point x prime. And similarly, for the vector potential. Okay, so far I have made no approximations. All I have done is made some assumption about how the sources are changing as a function of time. Okay, I haven't made any multipole expansion or any approximation whatsoever. These are exact solutions if the source's time dependence is purely harmonic. Okay? And again, the solution is just spherical wave emanating from the source points x prime weighted by the strength of the source at that point x prime. Okay? So now what we want to do is as we saw and we discussed, there are these three zones: the quasi-static zone, the induction zone, and the radiation zone. The moment, and from now on, we're only interested in we're looking at the electromagnetic radiation. So let's go to the radiation zone. All right, we're in the zone, and when we go to the radiation zone, we only have to consider the things that are going to fall off like 1 over r. Everything else is a correction. In addition, we have this approximation that the size of the source is tiny compared to the wavelength. Compared to the wavelength, in which case we also know k times x prime. X prime is something that tells me the size of the source. K is like 1 over lambda, that exponent is small. So the only terms that contribute to radiation, we only retain the radiation terms, are the following. So maybe I should write this here. So retaining so e to the I, so in this case, this thing is only going to be on the order, is only going to be about 1 over r, because we're keeping the radiation terms. And e to the I k x minus x prime is approximately e to the I k r times e to the minus I k r hat dot x prime. So that in the radiation zone, the radiation contribution to the scalar potential is equal to e to the I k r over r integral dx prime rho tilde at x prime e to the minus I k dot x prime, where k is k r hat, and the radiation contribution to the vector potential is either the IKR over R integral dx prime j tilde in units of c e minus I k dot x prime. So what we see here is that firstly, let's interpret, this is clear. When this is, we're looking at the radiation, we're looking at the stuff that goes like 1 over R. This expansion here is telling us that the wave accumulates a phase that depends, well, there's a dominant amount that depends on the phase accumulated from the origin, and then there's a small correction term depending upon where I am in the source. So if I'm a little bit closer to the source than the origin, then I subtract off a little bit of the phase shift here. If x prime is a little farther from the origin, then this is a minus, so I'll have a little extra phase shift. So this is the additional phase accumulated by the spherical wave. Remember, what we have here is we have this source. Each source point is emitting these spherical waves, and I see some superposition of them. And I have to add on the little extra phase shift or subtract off a little phase shift depending upon where I am relative to where that source is. And we're adding up all those wave contributions in a kind of interference. Yeah?
Why don't we keep more terms in the exponential? Or like, it seems like that's like you can approximate more.
Sure.
Beyond that.
You absolutely can. I mean, we're not, at the end of the day, of course, this is itself a power series, which will have many powers of x prime in it.
Yeah.
Okay? Let's see, where's that going to go? I have to think about that carefully, of how that contributes in the radiation zone.
Because it seems like if it's all inside like a complex exponential, then it wouldn't like affect, like it's a different reason from why you only keep the 1 over R term of the.
I agree. I'm going to have to think about it a little bit more carefully. To the level of approximation we're about to make, it's not going to make a difference because we're only going to keep that first order term, but what you ask is an important question. My recollection is that those terms don't contribute, but I don't remember why. But you may be right that they are there. Let me think about it some more and I'll come back next time with a clearer answer. Okay, so under this level of approximation, for whatever it's worth, which I think is actually correct, but I'm not positive, that this actually has all the radiation pieces in it, then what we see here is that the radiation term here is a spherical wave weighted by what? Nothing more than the Fourier transform, spatial Fourier transform of the distribution, evaluated at the spatial k vector given by k is equal to omega over c times r hat. I'm pretty sure that's correct. I just don't remember what happens in these other terms. So that says that the radiation part of the scalar potential is equal to the Fourier transform of this evaluated at k, and the vector potential is the Fourier transform of the current distribution divided by c. Making no question.
I was gonna say, I think those higher order terms only come in when you're looking at near field diffraction.
Yeah, they do. So that's really the question. I mean, there's different issues here. Here we're talking about radiation. There is the Fresnel and Fraunhofer regions, if we think about that. I mean, this is like a diffraction integral, right? Where you take the Fourier transform of your slit function or what have you. But what I'm trying to remember here is whether those other terms contribute to the radiation at all for this localized kind of. This is not quite diffraction. Let me think about it a little bit more. But I was thinking the same thing, but I'm not positive about that. We'll come back to it. Let's focus on this for the moment. Okay, so that's a nice formula. Okay, this is our radiation associated with this harmonic distribution in the radiation zone. So it might just be that that's the radiation, that the other terms contribute in the induction zone, which does include radiation, which is equivalent to the Fresnel zone in optics. That's probably the right answer to that. But in the radiation zone, when R is much, much bigger than lambda, then this is the radiation piece. Okay, so now we haven't yet made any approximations other than that we're in the radiation zone, where this is true. So now we want to make the multipole expansion. So let me begin here by just saying the multipole expansion told us that we required D to be much, much, much less than lambda, which is to say K times D is much, much smaller than 1. Okay? So, that tells us something about the nature of these spatial Fourier transforms. So, if we look at the spatial Fourier transform of our complex amplitude, this exponent we said is small because we're integrating over sizes x prime that are such that they're much smaller than the wavelength, such that this exponent is small. So the multipole expansion is equivalent to doing a Taylor series expansion of the complex exponent. 1 minus I k dot x prime plus minus I k dot x prime squared over 2 plus dot dot dot. That is equivalent to the situation under the approximation that D is much, much smaller than lambda, which is to say K times D is small compared to 1. And similarly, for the Fourier transform. Of this. So if we look at that more carefully now, we say, okay, those are the expressions of the sources. This is not the sources. What the heck am I writing? Yeah, no, I'm sorry. That is what I'm writing. Let's think about something else, which is, I forgot to include one piece of the puzzle here, is now given these potentials, what are the fields? So let's do a little aside here. The electric field in the far field, in the radiation zone, that's you. That's equal to minus the gradient of phi. Minus 1 over c dA dt. But we're talking about harmonic oscillation, so d by dt is equal to minus I omega in the Fourier domain. That's what we're looking at. Plus omega over c. Times I. So now if we plug in our expressions for phi and a for the radiation here, the gradient of phi is the gradient here. Again, keeping only the terms that go like 1 over r. We only take the gradient of the exponent, the gradient of 1 over r to 1 over r squared. That's not contributing to radiation. So this becomes minus ik r hat rho tilde of k plus ik j tilde over c e to the I k r over r. Okay? That's plugging in a and phi into the expressions that define the fields. However, J and rho are not independent. They are constrained according to charge conservation. By charge conservation, del dot J is equal to minus d rho dt. But if we now take both the time and spatial Fourier transform, that tells me that ik dot j, because in the Fourier domain, the divergence becomes dot product with ik, is equal to plus I omega rho tilde of k. So, rho tilde of k is equal to k over omega dotted into j as a function of k. It's spatial Fourier transform. So, what does this tell us? this says that the radiation, the electric field associated with this radiation, is equal to I k over c j tilde of a. That's this term. Minus I k r hat, rho tilde is equal to k r hat over omega dotted into j, where I wrote k, the vector, as its magnitude and the direction, which is r hat. All multiplying I k r over r. So let me factor out somewhere something got screwed up. Oh, there's an omega there, isn't there?
You just need
Yeah, that's not a
there is a C.
there's an omega. Where did I screw up? I screwed up somewhere. Get my notes. Don't try to do this in your head. Just screw it up.
I think you got one too many one over C's.
We have a k here. And then we have a 1 over c. This is correct. So that's all correct. That's got the right units and everything is hunky-dory. Now I plug in rho, and rho is equal to rho is equal to kr. Plug it in over omega. Okay, that's good. That's what it is. That should have been a C. That should have been an omega. Now I can write it. K over omega is 1 over c. So this is I k over c j tilde of k minus r hat dot j tilde So, what have we learned from this expression? What is this? This is the component of J that is transverse to R. This is what we call J perp, or J transverse. And so, we have a compact expression for the radiation, for harmonic oscillation in the radiation zone. To find the electric field associated with the harmonically oscillating current distribution, we take its spatial Fourier transform, and then we look at the component of that that's perpendicular to R. We subtract off the piece that is parallel. Remember, this is what we also saw if we had done this to start in the Coulomb gauge. We would have, from the start, said just look at the transverse piece. That's the only piece that we care about. This came from the scalar potential, and we just subtracted off. It was the vector potential was this was the scalar potential, the gradient of the scale. We just subtracted that off to make it transverse. At the end of the day, the field that we see can't depend on our choice of gauge. We did this in the Lorentz gauge, but it doesn't matter what gauge we adhere to. the magnetic field here is equal to I k over r j total of k minus r hat cross into j, which is equal to the radiation cross into r hat, as it must be. So, again, these expressions have not yet included the multipole expansion. I'm sorry, I made a little sidetrack over here. This just say, if I have harmonically oscillating charges and they are associated with certain distributions of rho and j, then this is the electric field and magnetic field associated with the radiation profiles. Now we can make the multipole expansion. And here it is. So now we can plug in for our J perp. We need to just calculate J, then take the perpendicular component. Under different levels of approximation when D is small compared to lambda. So let's conclude with that. So, to lowest order. J1. You just plug in that lowest order expression there. That's just equal to J. Okay, that's this part of the expansion and the expansion coefficient. And this is what we found, what we had in our discussion of the electric dipole, which is written here. We found that this was equal to minus I omega, the first derivative. No, that's right. The first derivative is minus I omega. So let's see. Which in this case, so this, we found that the electric dipole was equal. We had a harmonically oscillating time distribution. Remember, we had that funky integral that allowed us to compare those two if you go back to your notes. So this part is the electric dipole contribution. And now we have the solution. We plug that in. E rad is equal to IK, which is omega over C, so that's omega over C squared. We have omega squared over C squared P naught per e to the IK R over R. And hopefully that's still sitting here somewhere. There it is. And B radiation is equal to E radiation crossed into or the other way around, R hat cross that. Okay, so far so good. Let's look at the next order term, which we'll just begin now and finish next lecture. So now we have this term in the expansion. Oh, by the way, I should say, there's a jargon associated with this that you will see in talking about multipole radiation. They're given various denotations that are kind of arcane, but we still use them. This is sometimes known as E1, electric dipole, or electric first order electric. Electric dipole is called E1. Magnetic dipole is called M1. Electric quadrupole is called E2. Okay? So, let's take a look now at the next correction. Next term in multipole expansion. This next term here, J tilde as a function of K, is minus I K hat dotted into X prime J function of X prime e to the minus I K dot X prime. Okay? Integrated over X prime. So let's write this in component form. The ith component of this vector, this is dotted into this, so this is the ith component here. Dot this into this, use the summation convention, k sub j, integral x prime sub j, that's that dot product. The ith component of that is a function of x prime e to the minus I. K dot minus G. Okay, that's from this term. So, this guy is a tensor. Everyone loves tensors. It's going to be a new TV show. And then we do the summation over the index j with this. Now, when we see a tensor like this, we should break it up into its irreducible components. So this can be expressed in terms of a symmetric tensor and an anti-symmetric tensor. Obviously, you add them together, you get that. What we will discuss next time, just want to give you a little bit of a preview, is that this corresponds to magnetic dipole of the distribution, and this corresponds to the electric quadrupole. E2, M1. So the next term in our multipole expansion can contribute in the same order of approximation two effects: magnetic dipole and electric quadrupole. They are of the same order in the multipole expansion. And we'll finish up and look at the radiation associated with magnetic dipoles and electric quadrupoles. Next.